Hi, students. We're done with chapter 5 and we're done with chemistry and physics. So our fun little lab activity that we got to do on Friday, I'm so glad we got to do that. That we did on Friday, finished up what we needed to do with chemistry and physics. All right. So we're going into life sciences to finish out the school year because you start with biology next year for freshman biology. So it makes sense to finish with our life sciences or our biology pieces for you. All right. So we're in chapter 13, fossil evidence of evolution, and it starts on page 445 in your textbook. So in order to talk about fossil evidence, we need to know what a fossil is. Well, a fossil is the remains of prehistoric organisms. So these remains typically are going to be the harder remains, like the bones, because tissue is usually eaten by bacteria or things like turkey vultures. Have you guys seen probably turkey vultures around these parts? Probably seen turkey vultures. Let's get this size. And they go around and eat the tissue. The tissue cells usually don't get fossilized. All right. So those are things like your muscles, your tendons, all those things that are the soft tissue that are not the bones. Those usually don't end up being part of the fossil, right? So they take this information of the fossils that they have found and they create a fossil record using all these different fossils that they found in the record. Obviously, there are holes in the fossil record. The reason there would be holes is we can't even begin to know how many fossils we have not found. Does that make sense? This fossil record also, it has been used to prove the theory of Pangea, because organisms that shouldn't be in climates where they currently are indicators, and they match up with organisms from other continents in different climates. They can actually match up the layers and they can see that Pangea, plate tectonics, have really happened. So the fossil record has gaps in it, but there's a lot of information that is used from the fossil records. For example, they use the fossil record to help them see biological evolution as it has occurred in similar species. They would be species that are related to each other, like ancestors with each other, and they can actually see the changes in those species over millions of years. So biological evolution. So biological is the study of science, of life sciences. So biological evolution changes over time in their structure of their bodies. So extinction, there's actually been 5 mass extinctions. A lot of people don't even know that, and I believe you guys know that because we talked about that before. But there have been 5 mass extinction. So an extinction occurs when the last individual organism of a species has died. So there were some more extinctions in the year 2019. So how do we determine how old a fossil is? Well, remember when we talked about isotopes? Isotopes were the same element with different numbers of neutrons. Well, carbon 14, the isotope of carbon that is carbon 14, that has a mass of 14, is used a lot to determine the age of decomposing material or material that's been left behind. Forensic science uses it a lot because we know its rate of decay. We know the rate of decay for carbon 14. So with that, they can measure the carbon-14 isotopes and determine how old an organism, how long it's been there, how old it is. They can use it also, they use isotopes for dating the material around it, the sediments, the igneous rock. So isotopes are used for the dating of the material, so they can get an idea how old this material is. How old is this fossil? It's really important to know that to put it into a record in its correct position in the record. All right. So we're going to talk about how fossils are formed. I've got some visuals for you. We're going to look at mineralization and carbonization, molds and casts, trace fossils, and then original material. So we'll go ahead and move on to the next slide and start doing that, maybe. All right, the next type of fossil would be the molds and casts. So what happens is an organism passes away and sediment hardens around it. The organism ends up still decaying, leaving behind its imprint, creating a mold. And then if that mold refills up with more sediment, with a different sediment, then it becomes a cast. So this is your mold, and then this is your cast that came out of the mold. Trace fossils are footprints in the sand. So dinosaurs walked across the mud, and it later hardened and created traces of them being in that area. So they can look at the distance between the stride or the distance between the footsteps or the imprints and determine if it was, try to get a good idea if it was running or walking, and how deep the print goes down, how deep it goes down would help them determine the weight of the dinosaur. So if it was really heavy, it would be really, really deep. And if it was not a very heavy dinosaur, then it would just be a surface imprint. Okay. And then we have original material. And maybe you've heard of the woolly mammoth. The woolly mammoth froze to death while it was eating. So the temperature dropped so fast that the woolly mammoth died, and it was completely preserved. All of its cells and everything were flash frozen. So my understanding is they've even done DNA and everything else on him because he was so well preserved. They could see what he had been eating. They could check the contents of its stomach. Everything was frozen that fast. Maybe you've gone to a museum and you've picked up amber fossils. So what happens is an insect gets trapped in tree sap, and the tree sap hardens and it preserves it exactly as is. So it's all the original material. So that's how some fossils form that have the original material. All right, so now that they've found these fossils, they have to get them into the fossil record based on how old they are. So there's two ways that they use to date or express how old a fossil is. So they might use relative dating. Relative dating is simply saying, well, based on how close we found it to the surface, it's either young or old. They don't use specific time frames. They just use very general terms, younger, older, somewhat older. So we're at the surface here, okay? So this is where we are. So it would make sense that anything found close to us at the surface is going to be younger material because over time, layers and layers and layers build up. So as you move away from the surface, fossils get older. The deeper you go, the older that fossil is. So that's relative dating. Absolute age dating, they're going to use those isotopes to determine how old the material is as best as, within a range. They're going to get more specific. So they're going to use those isotopes of the elements that they know how quickly they decay. They're going to use those. They're going to use those to determine how old the layers are, the layers of igneous rock. They're going to use those to determine how old the sediment is. And they're going to then be able to get a more specific time frame for those fossils, how old those fossils are. So they can get them into the geologic time scale correctly. So if we look at this trilobite that I've pointed to with the blue arrow, how old would you say that one is? What would you estimate the age of that being? So it's between a layer that they've identified as 545 million years ago. MYA stands for million years ago. So 545 and 520 million years ago. So it's between those two. So I'll pause you, take a guess. So did you say roughly 532.5 million years ago, somewhere around 532 million years ago? The way I came up with that is the difference between these two numbers is 25 and is pretty much halfway between them. So half of 25 is 12.5. You add 12.5 to 520, you get 532.5. Dun, dun, dun. Okay, so 532 roughly million years ago would be what that trilobite, its absolute age dating is. All right. Okay, so now they've determined how old that trilobite is. They're going to now insert it into this geologic timescale. So we said it was probably around 532 million years ago. So it would fall into the Cambrian period. You see, period is up here, and which is part of the Paleozoic era. Do you see that? The eras, and then here's your Paleozoic. So it's part of that era. And in the Paleozoic eon. So there were 4 different eons that were broken down. There wasn't a whole lot happening until the Phaneozoic eon. And then the Phaneozoic is broken down into 3 eras, and then those eras are broken down into periods. So can you see all that? And this over here kind of tells you that this over here tells you, oops, kind of wrote over the million years ago numbers. That over there kind of informs you just how many millions of years ago that means. So a lot of you are familiar with the Mesozoic. You've heard about the dinosaurs being the Triassic, Jurassic, and Cretaceous periods. So you may be familiar with that. Well, this is what it looks like on the geologic timescale. So extinctions happened all along the way, mass extinctions, as I referred to earlier. Sometimes the extinctions were gradual, which means they happened over very long periods of time before the organisms all went extinct. Things that could cause gradual would be environmental shifts, maybe due to Pangea, the breaking apart of those plate tectonics, and then moving towards a change in climate until, and it gradually becomes something that the organism cannot adapt to. So then it becomes extinct, or it doesn't get a food source anymore, and then it becomes extinct. Or things can happen suddenly. So we know that in the time of the Mesozoic, there was a big meteoroid that hit the earth and caused a sudden extinction. So it wiped out the dinosaurs. So that meteorites, big, huge ones, and then huge volcanic eruptions also led to major extinction times. All right. So now this leads us to biological evolution. So here we have the aquus species, which we commonly know as the horse. And we can see how their structure from 55 million years ago, their front leg slash hoof went from being a paw to more like a hoof. So it changed over time. So you can see the gradual change, and then it became pretty um, common 5 million years ago for it to be the hoof structure that it currently is. So again, that is biological, that is evidence of biological evolution. All right, guys, so now you're going to use 9 of the terms that I've gone over with you, and you're going to come down to the bottom part. You're going to come into the bottom part of this, and like a chart-averse pass, what is that? Change over time, that would be the last slide that I just talked to you about. So you're going to fill in the words that go with it, and then after you have the words down in this bottom part, you're going to then take the letters and put them where they belong in the code. So I thought it'd be a fun way to practice the vocabulary. So I thought it'd be more fun than having to write it or whatever, write vocab or whatever. So then you put the terms up there in where the coding is. So for example, they've already done the I, and they found that it's number 7 is I. So then you go up here to I and you put your 7. So you'll do that with all the letters, and you'll fill in the top part. You'll fill in the top and the bottom. So have fun with that. Let me know if I can help you with any of it, okay? All right, so which step have you reached today? Well, um, I made it to the, yes, I did it, but it's not quite to my standards, but hey, I got it done, and I've learned a lot along the way. So yesterday, all day, they were showing us how to use Zoom um, to video chat with you guys and push out assignments. I'm not ready for that. So I upgraded this no, explain everything, and bought a subscription to it to try to make it a little more user friendly. And it took me hours to do this, you guys, because I don't know what I'm doing in here. So I never was that I won't do it. However, I did feel a couple moments of I can't do it. Um, you can see that there's some issues along the way with this. Um, so then it's like, okay, so how do I do it? Let me get back in the game. So I went to how do I do it? Let me get back in the game to, okay, I'll keep trying, and I'll just do my best. I can do it. I'll do my best, and I'll get it out to you. I know you feel that way sometimes, and a lot. And during all of this, with us pushing things out to you this way instead of getting to meet you face to face and work with you in the classroom, I know you're going to have some moments, but focus on the, okay, how do I do it? I'm going to try, and we'll all get through this. So I experienced this already. So Zoom meeting, I'm going to push out today for 11. So if you'd like to meet face to face, be available at 11 for a Zoom meeting. I'll push it out. It'll pop up in your email that I've invited you to my Zoom meeting, and then we'll just meet. You can have questions, or we could just say, hey, how's it going? And then you can go on with your day or whatever. Just kind of want to see y'all. So that's all I have for you. Take care and let me know. Reach out to me via email or Zoom me back if you figured out Zoom. Part of what I want to do in the Zoom is see if I can kind of help you use it. I used it a little bit with Mr. Schmidt a couple times yesterday, and so I was on your end of it, and I think I can help you a little bit with how to raise your hand and how to make sure you can see everybody that's in the chat with us. So, all right, take care.